far in this FDP program, all the participants have heard many lectures, learned many things. So in this lecture series, my addition is over the numerical methods for the initial value problems. Particularly, I am going to discuss the initial value problems consisting of ordinary differential equations. To start with the numerical methods, my idea is that first I'll briefly give the background of of such type of problems. So what happens is, see, whenever this rate of change of anything with respect to the other thing is actually a law, it's a very real life law, and every time we need to know that at what rate the thing is changing, right? So that if we interpret in the mathematical way, it is nothing but the derivatives. And with the help, the relation between derivatives of the dependent variables and the variables, other variables, always gives us the differential equations. Whether these are ODE or PDE, these are the different things. So whole and whole, what we have, that any real life problem we can mathematically model as a differential equation. And that differential equation we need to solve to know the solution of our real life problem, right? So for this type of, for getting the solution of differential equation, what we do, sometimes we use the standard known methods, which give provide us the analytic solutions, or you can say that the closed form solution of the problem. This is not always possible. So if it is not possible, it doesn't mean that we don't solve the equation, or other words, I can say that it doesn't mean that the problem is not solvable. Many times it is solvable, but with these standard methods, we are not able to solve it. So in such scenarios, we actually need the numerical methods to get at least the approximate solution of the problem. So that is why this part is important to discuss, that what are the methods which we can apply, numerical method, for finding out the solution of initial value problems. So let me start with a simple initial value problem. So just one simple example, let me take. So this is an example of which describes the motion of the swinging pendulum under these certain simple assumptions. So that problem we can describe as a mathematically we can describe as a, or represent as a second order ordinary differential equation, say d2y by dt square plus g by t sine theta is equals to 0, where this is the pendulum position, this is the vertical line, you can see. This is the vertical line. And this is our pendulum. So suppose this pendulum is making this theta degree angle for this, and the length of the chord of this pendulum is, say, L. So that is what it is written here. T is the time, obviously, y is giving the displacement here. And this G is nothing but the constant gravitational force which is there. So with that, we can describe like this. So this is a very simple equation. It is non-linear in nature, but if we take a even simpler case, like we say that, okay, the theta is very small. So for very small theta, what we know that sine theta we can approximate as theta. So in this case, it will become some linear equation, d by dt y by dt square plus d by t theta equals to 0. And this equation we can easily solve. We all know how to solve such equations. You can always write down this auxiliary equation. So standard method is available. So you can write down the auxiliary equation of it. And solving it, you'll get some value for this term m, this parameter m, and depending on the nature of m, the root, or which means the roots of this auxiliary equation, we can also, this is, okay, this is not y, this is theta. So I'm taking the displacement here. So this will be dt theta by dt square. So here, this is the second order equation, and you are writing in this way. So this we are solving, and we are getting the solution. So easily we can find it out the solution. So this is some equation, if I put one initial condition with this, saying that, okay, the theta means this angle theta at the initial time t naught is known and it is given by some constant value theta naught, say. So in this case, it will become the initial value problem, means after solving the equation, whatever general solution in the form of C1 something plus C2 something you will get for this equation. This is the general solution, you know. So for getting C1 and C2, we can make use of initial condition this and one additional condition. Suppose we know even the velocity of the motion of this pendulum at initial time, and which I am denoting by say theta naught dash. Then with the help of these two initial conditions, we can find out C1 and C. So this is the idea which we all know from the differential equation. So such cases we can easily handle, can get the solution as well. And the equation like this along with the two initial conditions in case of second order equation, we call as the initial value problem, right? So this is the one thing. And here now further, if I take further, I would like to take some example for showing you that it is not always the case that the equation has a solution. Okay, so equation may have the solution or may not have the solution. Or in for if you talk about the initial value problem, the same thing happens, that initial value problem may or may not have the solution. So why I'm talking about all these things with existence of solution and uniqueness of the solution of initial value problem, because before we go for applying any numerical method, it is very much important that first we assure that the solution of the problem exists, right? So that is why we need to start with the assumption that the problem which we are going to solve, or the problem for which I'm writing the numerical method, that is solvable, means their solution exists. Okay, so for that we should quickly recall the existence and uniqueness part of the initial value problem. So here I'm simply starting with the first order initial value problem. So in particular, I'm going to take the form of the first order initial value problem as dy by dt is equals to f of t y of t with the condition y at t not equal to y. So this will be the initial value problem, which I will focus on and will give you the numerical methods for it. Okay. So as I said, first we'll look into the examples where we will be able to observe that the solution may or may not exist for some problems. Okay. So first problem is the problem which describes the position of the particle changing every particle which is changing as per the sinusoidal. Okay, so in this case, what we can say that this dy by dt, the rate of change in the y, the position y of a particle with respect to time is proportional to sine of t. So I can write it simply as equals to some constant times sine t, right? And this equation along with some initial condition we have, so that we can talk about initial value problem. So initially at time t equals to 0, the displacement is say suppose v2, etc. any constant we can. So this equation is very easy to solve. You can easily solve it by integrating the both sides, and we know that the solutions come out as minus c cos t. This c is our given constant, and now I'm putting one constant here, constant of integration, which is generic constant in the solution, and this becomes the general solution of our equation, right? So this is becoming the general solution. Since we have the initial condition here, so we can substitute it and can get our C1. So if you substitute it, what happens? Y at 0 is 3, and that means minus T plus C1. So our C1 value comes out as 3 plus C. In the given constant C, it is appearing. So finally, we get some solution as particular solution as minus C cos T plus 3 plus C. Okay, you can rewrite in any of the form. That's not a problem. Okay, so this becomes the solution. So this is a problem, initial value problem, simple initial value problem, which we can easily solve and get its solution. Okay, and this solution is unique as well. Okay, but you should note here the one thing, that giving just the initial condition will not assure the uniqueness of the solution. In actual, the uniqueness of the solution depends on the two things, the properties of this function f, meaning here the property of this function particularly, okay, and also the nature of our initial condition. Okay, so depending on the nature of initial condition and depending on the properties of this right hand side function f, uniqueness can be assured. So sometimes what happens that the solution exists only on the finite interval. Okay, so this is the case, and one more example I would like to give you, which is considered as dy by dt equals to 2t y square with some initial condition. Here again the constant y naught I am taking as initial condition. So this again, it's a very simple problem, variable separable form you have. Just by integrating on both sides of the equation you can solve it, and finally with this you get the solution. I'm not solving it step by step, so but just telling you that okay, by just easily by integrating both sides you can get it. So I hope you can follow it. At any point of time, if you are not following me and you have any doubt, you can stop me and ask me the questions. So please feel free to ask the questions. So here the solution y of t will be nothing but 1 by y naught minus t square in the denominator. So this will be the solution. This is after substituting this initial condition I'm getting the particular solution. Okay. So what we can note here is if your value y naught, the initial value y naught is negative, what will happen? The solution will exist for all t greater equals to 0, right? You can just observe this solution formula and can easily note it down that if y naught is negative value, then solution exists for all t greater equals to 0. So for all time t, it is going to exist. But what happens if y naught is positive? Look at the denominator. If y naught is positive, then solution will not exist at some point. What is that point? This is t equal to square root of 1 by 5. Okay, because at this point the solution will blow up. Okay, so here the solution will not exist, and we can easily say that the solution will exist only for t belonging to the interval 0 and open interval 1 square root of 1 by y. So this semi-open interval, the solution will exist in this case. So that is what I mentioned, that depending on the nature of the initial condition or initial value, the solution, existence of solution, uh, we can see, right? So here in the finite interval for positive value of y naught, it will exist. And for negative value, for all values of t, it will exist. Okay. So on the basis of this existence of the solution and existence of and uniqueness theorem, I'm going to just recall here. So you may be knowing that if the function f and f sub y, these are continuous functions on some interval. So first of all, let me tell you what problem I'm considering. So just now I wrote y dash is equal to ft y of t. Okay, and with initial condition y at k t naught equals to y naught is my initial value problem. This is initial value problem, and it is defined say over the rectangular domain, and this domain I'm taking as a and b will be the constant here. So t is ranging from a minus t naught to a plus t naught. Sorry, t naught plus a to t naught minus it. Okay, so this is, and y minus y naught is less than equals to b. A and b are some constant. So this is my problem over the rectangular domain R. Okay. So this, for this problem, if the right hand side function f and its derivative with respect to y is going to be continuous function on the rectangular domain R, and moreover, if we know that f function is Lipschitz continuous. on the same domain R, and Lipschitz domain with respect to the variable y suffix. So we say that it is Lipschitz continuous on R with respect to the variable u. This initial value problem, which we have considered here, this is going to have a unique solution on the interval t, on the interval, closed interval, t naught minus delta to t naught plus delta, okay, where delta is some positive number, small positive number. Okay, so you can understand with this result that the solution is existing only in the neighborhood of the initial point, T naught Y naught. What is our initial point? T naught Y naught. So this is the rectangular domain. Here, this is your initial point, T naught Y naught, about which I am taking this R domain. So in this also, in this whole domain R, we cannot assure the existence of the unique solution, but in the neighborhood of T naught Y naught, we have the assurity for the existence of unique solution under the condition that f and fi is continuous and f function further is Lipschitz continuous. So this is the known result. So this guarantees us the known local existence of the unique solution of the initial value problem, right? If we want to know about the sorry, it is about local solution. So, but if we want to guarantee the non-local existence of unique solutions, means beyond this neighborhood, if the assurance of the existence of the unique solution is required, then there must be some additional, we should take some, the same conditions will be valid actually for but we need not to take anything over Fy. So with the Lipschitz continuity and the continuity of f function on R itself, f of R, f on R, we can state the global existence, or we can say that the non-local existence of the unique solution of the problem over the whole domain. So in this case, what you can assume that this is local case, and non-local existence, if we talk about, then here our domain will be something like that. So here I'm taking T is varying from this T naught minus A to T naught plus A in this part, say. On the other hand, Y is is a semester. Okay, so this is going to be extended for them. So this domain, this is T part and this is Y. Okay, so here our domain S will be a strip. Okay, so over this strip also we can assure the existence of the unique solution of this initial value problem under the condition that f is continuous on F and as well as it is Lipschitz continuous. So these two conditions will guarantee the existence of the solution of on this entire interval S, and this is called non-local initial condition. Okay. So this is the idea. So if you go back to the problem which I have just studied or just gave you this problem, here you can see that what is happening. Here you are having f function as fty function as 2ty square. Its derivative with y is nothing but 4ty. Both functions are continuous functions, okay, on some interval. And if you on the domain of this this initial value problem, in fact, for all t and y, it is going to be they are going to be continuous functions. And further, what you can note it down is that if this is the continuous function, then the solution will exist. But if you can check the Lipschitz continuity of f, which will hold here for this problem, you can check the Lipschitz continuity, then we can guarantee the existence of the unique solution, and that is what we are obtaining in this probability. And the solution in case y naught is positive, given for as a positive value, we are having the solution only on this small interval. Okay? So that is what it is saying, that in the small interval, it is guaranteed to have the solution, unique solution. Okay. So this from this example, you can see the application of this result. So this is about this. And now, okay, so I hope you know about the Lipschitz condition, so that I'll not discuss that what is the Lipschitz condition, etc. So basically, this condition we will just assume when we will start with the numerical methods for the initial value problem. Okay, so one more example before I start with the numerical method I'll give, where you will see that the solution will not exist. So here my problem is, say y dash is equals to e to the power minus t. This one, let me take different problem. So let me take t mod 1, okay, with some initial condition. Okay, so here what is your function? This is f t y, this is t mod y, right? So what we know is, uh, here you can understand that this function is not going to be differentiable at y equals to 0, right? So this is not going to be differentiable at y equals to 0. So we cannot find out fy. So this does not exist at y equals to 0. So it means this condition is not fulfilled, that fy exists here, and further we can check its continuity, etc., and can get the solution, right? So in such case, the solution will not exist. So basically, solution may or may not exist. That is, they always there with the differential equations. So with this, now let me move to the numerical methods. Okay, one thing also you may note down, that if you have this kind of problems, so can you solve it analytically? So far, whatever examples I took, all problems were solvable with the help of the standard methods, and we got some closed form solutions or the analytic solution. But if suppose we are with such type of problem, y dash equal to e to the power minus t, y to the power 4. So it is non-linear equation, and with the standard methods, it is not solvable. So in such cases, but this equation has a solution, right? You can check all the conditions with this function f. The solution will exist, but the another part is, the point is that we cannot solve it analytically with the help of any standard method. In such cases, we seek for the numerical, as I earlier mentioned. So let me now start with numerical method for initial value problems. So here, let me consider the initial value problem, y dash equals to f t y of t with the initial condition y at t naught equals to y. So with this, we'll start. So basically, numerical methods we can divide in two major categories. First one is single step methods, and second one is multi-step methods. Okay, so under single step methods, we can learn Euler method, backward Euler method, and I'll also discuss trapezoidal method. Okay, there are many other methods also, but I'll focus on in particular these methods. There's one another uh, standard method, Runge-Kutta, fourth order Runge-Kutta method, but that method will be discussed by some other speaker. So, even after including Runge-Kutta method, we cannot say that this list is exhausted. There are many more methods available, but in this in my lectures, I will particularly focus on these four methods under the single step methods. And as far as multi-step methods is concerned, again, there are several methods available which comes under this category, but I'm going to discuss here only the Adams-Bashforth method and Adams-Moulton method. Okay, so these two methods, particularly, I'm going to discuss under this. After these methods, I will discuss predicted vector methods also. Okay, and predicted vector methods will be nothing but it will be the combination of explicit and implicit method. Okay, so what are explicit implicit method during the discussion of different numerical methods, I will explain. Okay. So to start with numerical method of this problem, we can be noting by equation number 1. First, let's assume that the function f and its derivative with respect to y both are continuous on some domain, okay, on some domain say S, which contains the initial point t0, y0. Okay. With this assumption on f and fy, we guaranteed the existence of the solution of this initial problem. And in addition to this condition, if I can assume that f is Lipschitz continuous with respect to y, then it will further guarantee the existence of the unique solution of the initial value problem in some interval about the initial point. Okay, t. Okay. So with this assumption, we start and we will start with the Euler method, but for that, first let us understand that when we talk about numerical solutions, numerical methods for the solutions, getting the approximate solution of the equation of this problem, initial value problem, the approximate solution doesn't uh, evaluate as a continuous approximation. Instead, what happened? The approximation of the actual solution y of t will be obtained at the discrete points of the interval. So suppose here our interval for t is, time t is, say, t0 to t. So basically, we are looking for the solution over this interval. So what we'll do, we will first discretize it. So for the first step here will be, in general, for any numerical method, that we discretize the interval okay? So we discretize the interval as t0 less than t1 in any number of points we can discretize. So I'm just taking, say, n number of points. So first point will be same as this initial point, and the last point will be same as the end point of this interval. So this will be discretized, and then approximate solution at each point t0, t1, t2, etc. will be obtained, and we denote it by y0. Y0 is given, so y0, y1, y2, and so on, yn. These solutions, approximate solutions, are evaluated at the discrete points. Okay, so this is anyway already the given value. Y1, y2, yn will be evaluated at the points t1, t2, tn, which we obtain after discretizing the interval. So interval can be discretized with the constant step size, or we can even take the variable step size. But for simplicity, to understand all these methods, let me take the same step size here. So with equal spaced mesh points, what we say that here, this let me write down the place. So I'm going to consider the constant step size. Okay. Or you can say that I'm taking equally spaced points. Okay. So what will be the step size then? Then the step size will be h as capital T minus T naught divided by n. In case we divide our interval T naught comma T into n number n divisions, okay, n number of divisions or subinterval equals. Okay, so simply we can say that any Ti plus 1 will be nothing but Ti, T naught is h. Okay. I is varying from 0, 1, 2 up to, okay, so any point I plus 1 at point, we can simply calculate like this after setting our step size h with the help of the total number of subintervals which we are considering. Okay, so the numerical method which we are going to discuss in actual do not require the equally spaced time steps, but for simplicity, I'm just considering it, and in fact, it will be helpful for discussing the stability and convergence of image. So throughout the discussion, we will take the same step size. So equally spaced time steps we are going to consider. Okay. Now to derive the numerical methods, there can be different ways. Means we can adopt different approaches to construct the numerical methods. But what I'm choosing here is uh, is the so what I'm choosing to approach this numerical method for initial value problem from the perspective. I'm doing it from the perspective of the integral equations where we will approximate the integrals. So what do I mean with this is that if you have the initial value problem as y dash is equal to f of t, y of t, then I'll integrate it first. So means I'm writing the equivalent integral equation of it. And then whatever integral will be involved over there, that we will approximate. Okay. So with that type of approximation or with this perspective, we will approach to the different type of numerical methods here. Okay. So this is my equation in the considered initial value problem. I'm going to integrate it with respect to t from Tn to Tn plus. So with this, what I have is the following. And this is right hand side will be Tn to Tn plus 1, f of t, y of t, dt. Okay. So left hand side we can easily integrate and then write the value of it. So it will become f of t n plus 1 minus, sorry, y of t n plus 1 minus y of t n, that is equals to the same integral. Without knowing the function f, of course, we cannot integrate the right hand side. So that is called this whatever equation I'm getting here, this is called integral equation, right? And which is equivalent to the differential equation this. So solving this integral equation, we can solve this differential equation, right? So this is the equivalence property between the integral equation and the differential equation. So my approach here to construct the different numerical method to consider the equivalent integral equation and then approximate the integral involved in this integral equation. And what is that integral? This is the integral which we have to approximate. Okay. Because without knowing f, we cannot do, and f will be known only when we know the solution y, which is in actual not known, right? So how we will approximate it? Depending on that, we will get the different numerical methods. Okay. So first of all, we will derive the method which is known as a Euler method. Okay. So this method will be derived with the idea that this function ft(yt) we can simply consider as a constant. And what will be that constant? The value of the function at the point Tn. Okay. So which means I'm saying that this will be, we consider a simple approach here. We consider f function as constant, f of Tn by Tn. Okay. Because at Tn plus 1 step, we are calculating it. Okay. So previous step, this will be known, and therefore we can use it as a constant. So by setting this function f as a constant, say f at Tn y Tn, what we get the following. Y Tn plus 1 is approximated now as y of Tn plus integral Tn to Tn plus 1 f of Tn y of Tn. Right? And now since it is a constant term, this can be taken out, and then simply the constant will be integrated, and we will put the limits, and that is what gives you the approximate value here as y of Tn plus Tn plus 1 minus Tn multiplied with f of Tn y of Tn. Okay? So this is the approximate value here. Now if we use the another notation for representing the approximate value of the actual value of y at Tn, say, then we can write down the numerical mean. So approximate value, let me consider as approximate value of y of Tn, or you can say that denote the approximate value of y of Tn as y with suburb. Okay, so with this equation I can write as y with the fixed n plus 1 is equal to yn, sorry, plus Tn plus 1 minus Tn will become h, the step size, and then f Tn y. Okay, and this is known as the Euler. Okay, so this is the Euler. So graphically, what we are doing is simply you are having this. Suppose we have t at this x-axis along the horizontal axis, and vertical axis I'm considering say y dash, of which means f of ty. Okay, and this is suppose your curve. This is Tn plus 1. This is Tn minus 1 point. Okay. So basically what we are doing in this integral, we are trying to compute the area under this curve, this whole part, right? But instead of doing this, we are approximating it, okay, with this value, which will be this part only throughout this interval. So this area under the curve, we are just approximating or calculating with the help of these areas. So of course there will be some error involved in it, okay? But it is the approximation, and which gives this result. Okay, so that is the idea. In other way, geometrically, this method can be understood as follows. This is t-axis, and now I'm taking y over here. This is my function here. Okay, so this is suppose Tn value, and this is say Tn plus 1 value. Okay, so basically geometrically what is happening here, it is giving us the approximation of this curve y. Here this is the curve y of t. Okay, this approximation is, we are approximating it this curve y in this interval, this will be the curve, and this we are approximating by this thing. Okay, this particular line, which is nothing but the tangent to the curve at point Tn. So basically, y at Tn plus 1 in actual should be this particular value to here, but we are approximating it by this line, and therefore it remains like this. So this part is actually we are evaluating. So you can say that AB you are evaluating, and that we can easily calculate because AC will be same as y at Gn. Only this BC part we have to calculate it, and this BC will be nothing basically you if you calculate it. This okay, this is the slope which is given by f of T and y at Gn. Okay, and then this is nothing but h value, and that is why it is coming h into f. This is just the Pythagoras theorem. Using the Pythagoras theorem, you can easily substitute it. So this is the approximation here it is happening. So it is observed that this approximation is nothing but a stepping forward along the tangent line to the curve y at the time Tn. Okay, as I'm sure I have shown here. This is the stepping forward. Okay. Now let's take one example for the Euler method. So here I'm considering the initial value problem. Y dash is equals to 1 minus 3t y with the initial condition y at 0 is equals to 1. So exact solution can be obtained here, and this is a simple problem so that we can compare the numerical solutions with the exact solution. Okay, so this exact solution for this problem will be nothing e to the power 3 minus 3. Okay, and with this you can solve this is kind of exercise, anyone can do it. Okay, and if now we apply the Euler method, if we apply, to get the approximate solution, what happens? So Euler method says that at n plus 1th step, the solution yn plus 1 will be yn plus h, f evaluated at Tn yn. What is f here? F is 1 minus 2t into 1. At Tn point, I can write it as 1 minus 2Tn y. Okay, since f is this. So this is the Euler method, approximate solution obtained with the help of Euler method. Okay, now let me consider the step size. So let us solve it by taking the step size 0.25. Same thing you can do with the different step size 0.125, 0.0625, etc. Okay. So first, if you take 0.25 and you take the discrete points like T1, T2 up to T12. So what we have, because the step size is fixed here 0.25, so we can say that here we will be having the discrete points T0, T1, T2, and so on T12, right? Because your step size h is nothing but final. Here interval is 3, 0, 3, so 3 minus 0 divided by n. So n is equal to 3 by 0.25. Okay, so that gives you the 12 number of points. So n will run from 0 to 12. Okay, so 12 intervals are there. And you know that it will be 0 and this will be 0.25. Likewise, we can calculate all this. Okay, now what is our job? We'll substitute all these values at discrete points, different discrete points into the Euler method approximation, and we'll get the approximate solution at each point. Okay, so with this, you can find out all y1, y corresponding to t1. At t1, you can get y1. At t2, you can get y2. Here, similarly, y12, you can obtain. So if you want to calculate y1 with the help of this, it will be y0 plus h, 1 minus 2t0, y0. We already know what is t0 and y0. T0 is 0, y0 is 1. Okay, these are the given values. So with the help of that, we obtain it simply as 1.25. At 0.25, once you substitute every value, you will get this slide. Similarly, y2 you can calculate. So after substituting all the values of y1, t1, etc., y1 you have calculated in the previous step, substituting all these, you will get the value here as 1.40625. So likewise, we can tabulate all the things and can see that what are approximate solutions we are getting, and exact solution also you can tabulate. So here Tn you can write, here Yn you can write, then in the next column Ytn you can write. So 0, 0.25, 0.5, likewise you can continue up to the last one, and correspondingly you can write down the values over here. So here it is. One exact solution you can obtain with the help of this formula which you already have. Okay, and then here is one, and then we can calculate the error in the last column, which will be the absolute value, which is the difference between the actual value and the approximate value, and we get the absolute value of it. Okay. So likewise, you can list for it, and once we list all of this, so manually, of course, it includes a lot of computation and takes a lot of time, but with the help of writing the program, you can compute it. You can even draw the graph and can see that what is the pattern in the error. So here, what we observe that in this case, the error comes out as 0.0438, and corresponding to this we can fill. Okay, so I am not writing everything. So 1, 2, 2, 2. So as this is, we are moving in the interval, okay, we are seeing that the error is increasing. Okay, so with this, if you among these, if you take the maximum error involved, that will give you the L infinity error. Okay, in the case when a step size is 0.25. Similar steps you can follow for finding out the error, L infinity error, once you change the step size as 0.125, which is half of the previous step size. And also you can do the further computation. Further, you can reduce it, half of the step size you can take, and can calculate the errors and write down the L infinity error. And then if you compare all these L infinity errors corresponding to the different step size, what we see is the following. So when we take a step size as 0.25, the L infinity error, or you can simply say that the maximum absolute error, it comes out as 0.23047. When we take 0.125 interval, 125 interval, what happens? We have 0.10967, then 0.0625, then error comes out as 0.05405. So likewise, we can list out, okay, and what we observe that the error is actually decreasing here if we are taking the small step size, okay, and see this step size is half of the previous step size, so almost half of the error we are getting as a result also. Okay, so error is also becoming lesser and lesser. Okay, this is what is expected here. Okay, but at the same time, we also observe that the involved error here in this particular method, known as the Euler method, is not very good. It is just of order 1. Okay, so what is the meaning of order of the order of this error order, etc., or truncation error? How do we define that? We will see. Okay. Before that, let me give you the backward Euler method. Once I define this backward Euler method, then we will go for the truncation errors. And from there, you will understand that what is the order of the method, numerical method, and how we calculate the local truncation error and global truncation error. Okay. So in backward Euler method, we are going to now approximate the integral, okay, by setting it as a constant again, but this constant we will now take as the function f at the point t n plus 2. Okay, so if you recall the Euler method which we just established, here integral is approximated. We're setting this f function as a constant f at tn by tn, but in backward Euler method we will set it as f tn plus 1 comma y tn plus 1. So that will give you the Euler method. So here the idea is that f of ty we are going to approximate as f tn plus 1 y at tn plus 1. So if we do this, what happens? The same procedure will follow. Your integration thing will give you y h tn plus 1 is equals to y h tn, and then plus integral tn to tn plus 1. Now the function is approximated like this. Okay, and in turn, this is the approximation. So this will give you, this part alone will give you h times f of tn plus 1 y of tn plus 1. So that is the only difference here. So as the approximation, you can write it as yn plus 1 equal to yn plus h f of tn plus 1 y of tn plus 1. So that is known as backward Euler. Okay, so what is the difference? Here, this method defines yn plus 1 implicitly. Okay, so sorry, this is not tn plus 1. This is with c, yn plus 1. So this is known as backward Euler. Okay. So here yn plus 1 is defined explicitly. It is meaning it is present on both sides. While in the Euler method, it is defined explicitly. So that's why Euler method is known as explicit method, while the backward Euler method is known as implicitly, because of the presence of yn plus 1 implicitly in this method. It is known as implicitly. Okay. So of course, if f is complicated, then it will be difficult to get yn plus easily from this expression. Okay, especially when f is non-linear. If f is linear, easily we can write the expression whatever you'll get after using this method, which will separate yn plus 1, or which gives you the explicit form of yn plus. But if f is a non-linear function, then it will be complicated to get yn plus 1 from this. So in such cases, the idea is that we use the iteration techniques like Newton-Raphson method or secant method we can apply. We can do the iteration for yn plus 1, and whatever the final iteration will get as the value, that will be used here to get y, and finally the approximation with the help of backward Euler. So this will be the idea in case you have the non-linear function of in your problem. Okay, but to example, for simplicity, let us first see this application for a simple PDE. The same problem which I have just taken, you can see that if you apply this backward Euler method, is there any improvement? Okay, but the truth is there is not much improvement. You'll get almost the similar or marginal difference of the error. In error you will see, or better error estimation will come. Otherwise, it is also going to give you the similar thing. Okay, so here when you apply this method, what the expression you will get, yn plus 1 is equals to yn plus h, and f function is this. So this will become 1 minus 2 tn plus 1 yn plus 1. It is a linear form. So easily we can write down yn plus 1 explicitly as 1 over 1 minus h, 1 minus 2 tn plus 1 y. Okay, so you can easily find it. Similar steps what you have done in the previous problem, but when you use the Euler method, here also you can list down all the approximate solution along with the actual solution. Okay, for the step size. Okay, and then you can see that this is not the same problem, I guess. No, it's the same problem. Okay, so we can compare. Fine. So here, whatever error you will get is if for 0.2 interval, this is not, I have not, okay, so this is the problem for which you can solve. And if you get the solutions for h is equals to 0, 2.5, again you will calculate Tn, Ya, and Yf actual, and then the difference. So when we list, what we observe is there is a slight improvement in the error, otherwise it is similar. Okay. So for example, here, if 0.25, here we are getting 0.00438. In case we calculate the value at 0.25, approximate value as at 0.25. Okay, so error involved with the help of this Euler method is this. And when you use the backward Euler method, you will see that it is almost similar, something like 4, 2, something like that you will get. Okay, so let me not write down everything here. Just as a note, you can put that there is slight improvement. Then we apply the backward Euler. Okay, so this is actually the case that it does not much improve. Okay, so only the slight change will error, and also it shows the same pattern. Like if we take, it shows this pattern that there will be that if you reduce the step size, means if you make it half to the previous one, then the backward Euler method, in backward Euler method also error get comes down as the half of the previous one. Okay, so in here itself, okay, for L infinity error, at least I'll give you. So this is because of Euler method. So for backward Euler method, what we are getting is 0.19036. Here we are getting 1.1017. So you can see that there is a slight difference. Okay, order wise there is no difference, but yes, in magnitude there is a slight difference. Error is slightly lesser than the previous method, but the decrease in the error as you decrease the step size, okay, is showing the same pattern, that it is becoming half, error is becoming half of the previous one if you reduce the step size half of the previous one. Okay, so in this way it is going on. So this is the backward Euler method and Euler method concept. So do I have time further to discuss the truncation errors?
Yes, madam, if you want, you can take the time and let's say another 5-10 minutes.
Okay.
Yeah.
Okay, then in another 5 minutes, I'll just introduce that what is the meaning of the arrow, and then the details I'll give in tomorrow's lecture.
Okay.
Okay, so this is what we learned, that these are the two methods which provides the approximate solutions, and of course there is some error involved. So when we say that some error involved, we should understand that what type of error these are and how do we calculate. And before that, we should also understand that Euler methods, in practice, we use rarely. Uh, but the idea of learning this method is that these are very simple to understand, and the understanding of this Euler method or construction of this Euler method actually nicely explain the principle of the more advanced numerical method. It helps us to understand those principles. Okay, so that's why we first learn Euler method. Okay, some advanced method it goes later on. So as I said that we are going to now talk about that what is the error. So So the main question arises here is that what is the guarantee that the approximate solution will approach to the actual solution? This is known as the convergence. Okay, so what we can, in other words, I can say that the when the whether this solution, no, approximate solution will converge actually to the approximate solution if we compute it with the help of the numerical methods. Means if your h is approaching to 0, the step size is going to be smaller and smaller, whether the approximate solution yn comes out as the solution at the final step time t or any step time t. Okay. So so the question, so as I said, there are some questions. Does yn convert this? First question is, does yn convert this to the true value? Okay. Second question is, how quickly it will convert? If it converts, how quickly? Does yn converge over the interval? Okay. And the third part is, how small the step size should be needed to achieve the desired accuracy. Okay, to achieve the desired accuracy. So these are the three questions immediately come into the mind when we use the numerical method. Okay, so to answer these questions, we have to understand the relationship between the error and the chosen step size h. Okay, and that is what we will now see. Okay, so this comes under the global and truncation errors. So the error meaning here is error which is this is the difference between the exact solution and the approximate solution obtained using the numerical method. It is a very simple definition. Okay, so we can say that the global truncation error is nothing but, this is about global truncation error. Okay, so global truncation error means nothing but the difference between the actual value or actual solution at the step n and the approximate solution. Okay, and we can denote it by say capital E with strict n. Okay, and this we can write for all steps, all mesh points, or you can say that it's three. Say I'm having 1 to 2 endpoints. Okay, so this is the simple thing. This is very usual manner. We always look for the error, and that is what we have done in the examples as well, right? But here the thing is, inherently this yn, this part yn depends on the approximate solutions obtained in the previous steps. What are the approximate solutions? Yn plus 1, yn plus 2, like, and the previous steps, whatever the approximate solutions we have obtained over which this yn will. Okay, so it means we have, if we want to know the solution, we know the solution exactly at these previous points, n plus 1, n minus 2, etc. Then the error you will calculate on the next, in the next step. Okay, that will be the error involved in that particular step. Okay, this is the global error for the numerical method, but this method in actual involves many steps. So at each step, when we calculate the approximate solution, that itself will involve some error. Okay, so this error involved in each step is actually known as the local truncation error, and that we obtain assuming that the previous steps we have the exact value of the solution. Okay, so that part, that local truncation error, we write as y at Tn, that the actual solution, minus yn's. Okay, and we denote it by En. And y, as I said, this yn star will be obtained using the actual value of the or actual solution in the previous step. So we can say that it is nothing but y at Tn minus 1 plus h f of Tn minus 1 comma y of Tn minus 1. In case of Euler method, I am writing. Okay, this is for Euler method. Okay. So there is a thin line difference between these two things: global truncation error, local truncation error. But in simple manner, what we can say that local truncation error is the error involved at each step of the numerical method, while the global truncation error is the error which is in total we have or we obtain for the numerical method. So this is the accumulated error. Global truncation error will be the accumulated truncation error. You can understand in this way. Okay. So this is other than these two errors, there could be the round off errors also, because computer only have the finite precisions. In fact, if we calculate manually, that in that case also, we just stop our computation after some after taking some digits. We stop after some digits. Okay, after decimal, we take just certain finite number of digits and stop it. So it gives us some round of error. Okay. So but what happens if you take the sufficiently small step size h, then global truncation error will dominate. Okay. And dominate the observed error, and then we don't really much, we need not to much bother about the round of errors in such cases. Okay. So for appropriate step size of h, we just seek for the global truncation and local truncation error, and then the global truncation error. Okay, so how do we find the local truncation errors, or what will be the bound of the local truncation errors? Is basically what is the order of these errors, local truncation error and the global truncation error. That part I will discuss in my tomorrow's lecture. Okay, so with this I close today's lecture. Thank you so much. If you have any doubts, please you may ask.
Yeah, thank you, Professor Shruti, for a very wonderful lecture. So, if participants have any question, they can write in the chat window. So if there is no question, let us again in this class, no doubt. Okay, thank you, Satyendra Prasad, for writing to us. There is no doubt available. Okay, thank you very much. So let us again thank to our speaker, Professor Shruti Dubey. And Professor Dubey, may I request you to send your, okay, you have not used any PPT. So, okay, we are recording all the lectures, and the link for those lectures will be available to the participants on the Canvas platform, so that those who have missed the lecture due to any reason, they can again go through the lecture. So participants, the link of this lecture, the recorded lecture at the YouTube channel, the link for the same would be available by tonight at the Canvas platform. So those who have missed some part of the lecture, they can again go through it. And now we will break for 5 minutes, and after that we will start another lecture by Professor Ritesh. And now it is 5:15. We can come back at 5:20. So 5:20 we will be starting another lecture by Professor Ritesh. Thank you.
Yeah, I'll stop sharing my slides and then I'll sign. Thank you,
Yes.
everyone.
Yes, yes, madam. Yes, thank you.